Good afternoon, everyone. My name is Jason Knapp. I'm Chief Science Officer at Riverain Technologies. My talk today is about how we can use synthetic data to substantially improve how AI gets built. A little bit about Riverain. We're a chest health company. We use AI to build applications for chest X-ray and CT. Our products are used throughout the world, including at many leading academic institutions. Our two product bases are clear-read CT and X-ray. If you've heard of us, it's probably due to our ability to suppress normal anatomy while leaving disease in the image. So I provided a talk on Monday, and we hit on several key issues, things that motivate the use of synthetic data. The first thing is the sensitivity to acquisition. This is an issue that still plagues AI. So every 2 weeks or 2 months, you see an article that says AI cannot be reproduced, the issues with repeatability from one device to the next. The other issue was weak supervision. So using AI where you provided very weak labels, such as there's a pneumothorax in the image, without actually telling it where it is a known issue as well. So at Riverain, we use synthetic data to solve a whole host of these problems. And lastly, we talked about the importance of hypotheses. So the idea that you can use synthetic data to actually fix issues when they arrive. At Riverain, we take the problem of acquisition variability head on. So it's somewhat, you're used to seeing things like image reconstruction, but as it turns out, AI can be used to solve the problem of acquisition variability. So you know before you put any system in the field that there are a whole host of devices across the globe. And you would be remiss not to take account of this. So in our systems, we developed this technology that can take any scan from any patient, from any device, and run it through a process that the resulting volume or image looks as if it came from a single scanner. And what this enables is repeatability. So you can plug in your AI and it can just run. Similarly, what it also does is it allows you to extend your range of application, whether it's extremely noisy data, which is common in oncological patients, or very thick sections that may happen in full body scans. So the idea of using AI to factor out normalization is sort of a cornerstone of what we do. And not just for CT, but for X-ray as well. So if you look back the last 5 years, and you might ask yourself, well, where did a lot of these supposed breakthroughs go? And what you believe is many of them are due to a lack of repeatability. In other words, the machine learning part was done fine. What the problem was, though, when you tried to transfer those models to different devices, it didn't transfer. So again, at Riverain, we take this problem seriously. We build this into all of our applications, which is why when we install something anywhere in the world, it just works. So using synthetic data, it has a whole range of uses, and some are obvious, some are less obvious. The obvious ones were gaps in the data. So you sample the world, you collect data, and unquestionably there's going to be many gaps in the data, samples that you would like to have but do not have. Another, just perhaps the most important issue is bias. So if you sample data from across the globe from different scanners or different patient populations, any bias in that data will be in a model. A model is nothing more than a compression of the data set. So what we do with synthetic data, you solve problems such as the labeling issue. Right? If you give 3 radiologists a single scan, you ask for a diagnosis, it's very common to get 1 or 2, maybe even 3 different results. So if you can accurately simulate disease, then the uncertainty associated with labeling is removed. Another important aspect is the ability to control what the AI pays attention to. In other words, you want to get the right answer for the right reasons. And then lastly, this idea that if I find an issue, what do I do? I mean, the typical approach is to just add it to your training pool. But all that would really do is fix the sample, not the issue. So simulation can address these issues. So here's a small sampling, covering the spectrum of disease. So in lung nodules, there's a whole variety of patterns. It's very complex. You have a range of sizes, texture, cavitation, and so forth, and location. You can take the same nodule, and depending on where it's at in the lungs, the level of difficulty varies. So with synthetic data, you can control for all these variables to make sure that the AI actually works in different circumstances. Not just for lung nodules, but for a range of applications. So here I'm showing an example where a single patient with a normal, healthy aorta was used to synthesize a range of different diseases, okay, which can then be used to train a subsequent AI to find these diseases. And to be clear, when you use synthetic data, the only thing that matters is the performance on real data. So you might ask yourself, well, what's the catch? Well, what you get in exchange when you have 1,000 cases, if you use 900 for training the AI, you're only left with 100 cases for validation. And this is sort of the opposite of what happens in medicine. In medicine, you start with a small hypothesis and use many samples to validate. But in machine learning, you generally use most of the data to train the model and very little to do the validation. And again, this is perhaps why so many results don't hold up. Simulation does other things as well. So as I mentioned, the problem of labeling. So here I'm showing a particular example of before and after the insertion of a synthetic nodule. So one is a ground glass, one is a part solid. Having radiologists ground truth this is a notorious difficult problem. But through construction, you have no uncertainty. You know what the nodule is. And so what this enables is new applications. So this is a sort of zoomed in chip of what we call vessel suppress. It's part of our ClearRead CT product. And what you're seeing is a real nodule with superimposed vascular structure. And then on the right, you're seeing a true part solid lesion. So what you want to notice is that the technology is able to decouple, separate out the true vessel, yet also preserve solid components. And so what this does is it enables a piece of technology that does something that has not been done. So you're not just helping detect nodules, you're not just going to help segment them, you're actually going to enable them to be typed. And that's a big deal because depending on the type of lesion, the treatment and therapy can be quite different. So again, when you know something about the world before you build this technology, you should exploit that. So you know, for example, nodules in the apex is more challenging. It's more challenging for people, therefore it'll be more challenging for machines. So by constructing such examples in disproportionate ways, you get high reliability. For example, here's a real nodule that's subdiaphragmatic. It's quite large, but yet hard to see. So the AI, it finds it with high precision. How is that? Well, it's because it's seen this type of scenario many times. Similarly, this isn't just about nodules. Pneumothoraces. To continue to pick on weak supervision, you might have known about a few years ago there was a big contest where all these models and lots of energy and effort was spent on training AIs to find pneumothoraces in a scan. Well, what turns out to be the case is that most of these pneumothoraces were treated. So what happened is you had a bunch of models that were very good drain tube detectors, but not very good at finding pneumothoraces. So by providing precise location information via simulation, you under the hood you have a technology that can get the right answer for the right reason. So you want to give this technology, you want to give it more to do. You want it to not just label the image, you want it to find where the signal is, and from that you then derive the prediction. Turning our attention back to CT, here's an example of a patient before and after the insertion of a synthetic embolism. Doing this you're not going to convince a radiologist to label emboli for you. That's a completely arduous task. It would take forever. But through simulation, you can do this quite effortlessly. And as a result, build things that, when applied to real data, really work. You don't want to take the slice and say there's a clot here. You want to actually know where the clot is so that the decision is made. Extending this same idea to a host of diseases, here you're seeing an example of an aortic dissection. So, same kind of process that we follow. Build out a stack of synthetic data, train models, apply them. Aortic dissection, there's not a lot of this type of data in the world. It's a very rare condition. So how can you build technology that works on this when AI and deep learning needs lots of data? Use synthetic data. So this is a real example. And the other exciting thing about AI is that when you can do and build this way, it allows you to create new types of applications. So here's an example of a stack of things. So on the left, we see a segmentation. So this is where the aorta itself was segmented through a neural net model. And then subsequent to that, the center line itself was drawn with a neural net. So all this was built with synthetic data and then applied to a bunch of real cases, and the results were excellent. So it works, it transfers. So in summary, the problem of making sure that you have reliable AI can really be solved if you do the work. Data synthesis is not an easy problem, but it is, we believe, the right approach. For many reasons, one of which is that you get to do real validation. If you find an issue, you can fix it, and fix it in the right way. So we believe that what you're going to see in the coming years is more and more of this, more of the same, not just in healthcare, but across the globe, across industries. This is going to be the biggest topic that there is. So with that, I will end the talk. We would love to discuss anything else, so you may come to our booth and ask questions. Thank you.